Thank you. So let me remember what was the main problem that I was going to address last time. So it was lower bounds for the what we call the determinantal complexity of the permanent. So the notation is dc of n, determinantal complexity. Okay, so you remember it was the minimum size of a determinant in a matrix in a affine expression in the entries of the matrix, whose determinant gives you back the permanent. Okay, but the main conjecture being that this is not bounded by any polynomial. So today I want to give you an idea, or a rough idea of the program that has been initiated by Manivel and Laurent. Okay, which hopefully will allow to find new bounds on these determinantal complexities. So the program has not been successful yet, let's say, but at least it initiated lots of interesting mathematics, I think, and lots of new ideas have arisen, so it's really worth thinking more about that. So the strategy is, again, trying to involve as much as possible algebraic geometry and representation theory, and try to use these as tools that we know can be efficient in some situations. So let's try to reformulate the problem. Slightly. So what we want to do is, so again, write the permanent, let's say in M, for M by M matrices as a determinant of a matrix of size n, which is affine in the entries of X. Okay, so maybe first remark is that you can get rid of this affine transformation. You can make it simply linear. Okay, so first we make T linear. I mean, if we have if the ij entry of Tx is something like something linear plus constant. This is what is an affine map. It's just add a new variable, y, and we plug it inside the expression to make it linear. Okay, then what's the result of that when we compute the determinant of this new matrix? Okay, well, now this is the result now will be homogeneous of degree n. Okay, because we have a linear matrix. And we know that if y equals 1, we get the permanent, which is homogeneous of degree m. So the only possibility is that we have, when we do this operation, the permanent multiplied by some power of y, which makes it homogeneous of the relevant degree.
Okay, so x is a matrix, y is a scalar, right?
Y is just another indeterminate. So extra indeterminate. Okay, so
okay, yeah.
Yes, not a matrix, just
Yes.
one extra indeterminate. Okay, so we have this expression. So we have not exactly the permanent, but this expression, which is usually called the padded permanent. And maybe I will denote it from n, upgrade it to degree n. Should be x1. Okay. So just a little trick to work with homogeneous polynomials, which would be better. So then we look at the determinant, that n. So that's a polynomial in the entries of a matrix of size n. So we have n square entries. Okay, but I added one, so I will consider this as the polynomial in n squared plus 1 entries. Okay, so this is a notation for the space of polynomials of degree n in n squared plus 1 entries. And now what am I doing when I apply the transformation T? Okay, so I'm just making a change of variables, a linear change of variables. So I'm using here the action of the linear group in n squared plus 1 variables. Okay, which I will denote by G. Okay. So I'm not looking simply at the determinant, but at the orbit of the determinant under the action of this group. Okay.
So the determinant has only n squared.
Yes, but I see it as a polynomial in. So the determinant does not involve this new indeterminate, but still I can consider it as a polynomial in one more variable. Okay. And now what I want to do is express this padded permanent as something which is the result of this operation. Okay, so something in this orbit. Okay, so this is the question here. So it's not exactly the question because there is no reason for this transformation T to be invertible actually, just a matrix. So it could be singular. Okay, but of course the group G is an open subset of the set of matrices. So in fact if we have something like this, the permanent for sure will be in the closure of the orbit. Okay, so the question is maybe whether this one. Okay, so there's some issues here because we don't exactly know what is this closure. What do we need to add to this to get the closure?
Do you want to write orbit up there or n times n? So
yes, so for this one. But the question is does the padded permanent?
okay, but the original question is not whether this padded permanent is in the orbit, but something like m dot z n.
Okay.
Because that's easy to see that from
So that was what I was pointing out. So if you count this by m, so the original question is indeed that the permanent, does it belong to this space? So determinant transformed by some linear transformation. And if you want to look at this question using algebraic geometry, it's better to go to the closure. Okay, so my observation was that this is contained in the closure. Okay, but it is somewhere in between. We don't know precisely. We know it is not the closure. We don't know exactly what are the differences, but so the question I will consider is whether this one, when is the padded permanent inside the closure of the orbit of the determinant? Okay, and so equivalently we can apply also the group G to the padded permanent and look at the orbit. and take the closure. So the question becomes essentially this one. We have two orbit closures under the action of this group. And the question is, does the orbit closure of the permanent, of the padded permanent, is it contained inside the orbit closure of the determinant? Okay. So why is it better to reformulate in this way? Because we have we can use now algebraic geometry. We have these closures are affine algebraic varieties. So we can use tool from algebraic geometry. And we have this group. So we can use there are many tools in group actions and representation theory. Okay, so more weapons to attack the problem. Okay. So what can we do now? So in general, we have two. So this is in this big space here. Maybe call it Vn. Okay, so we have two algebraic subvarieties of this space, and we would like to distinguish them. Are they separated, or is one contained in the other? So there's what could we do? The most obvious thing would be to say that if this is not true, so if we don't have this inclusion, so what it is? So these varieties, they are defined by the set of polynomials that vanish on them, the polynomial equations. So if we do not have this inclusion, this would mean that we can find a polynomial which vanishes on this one but does not vanish on this one. Okay, so can we find? So we should be able to find so a polynomial P vanishing on this, but not on the orbit of the padded permanent. Okay, so this raises the interesting problem to understand the equations of the orbit of the determinant. So I don't know much about this question, but this could be a strategy. So the strategy that we try to use will be slightly different. So what we want to do is really use the fact that we have this group action, and the varieties we want to understand, they are closures of something we really do understand, because it's just the action given by the action of a group on the points. So this is what we understand best. And that's what we would like to use. So the other strategy would be to look at functions. And these orbits, and these orbit closures. So here I have to explain a little bit what can happen. So there are some subtleties here on what are functions on an algebraic variety, and you have to understand this to really understand the problem. So we have the notion of okay, so let's say an affine. So it'll be very basic, but an affine algebraic variety, we can see it, as I said, as a set of zeros, defined by the zeros of some polynomials. Okay, so affine algebraic variety, it would be Y. It can be realized as a Zariski closed subset. of some affine space V. Okay, so you have Y inside of V, given by a set of solutions of some finite collections of polynomials. Okay, the point being that a priori there are many ways to take your preferred affine algebraic variety and embed it in some affine space and find some polynomial equations which define it. What you can look at is the space of polynomials. So this is the notations for of the field of complex numbers, polynomials in V. And we can restrict them to functions called regular functions on Y. Okay. So this is a surjective map. And the point is that this object here, which a priori is defined in terms of V, so in terms of the embedding, does not depend on the embedding. So this is completely intrinsic. Okay, so we have these regular functions on Y, means that we can represent them as restrictions of polynomials in V. And if we have another embedding, we will have other ways to represent them as regular functions on another space. So this is the case of affine algebraic varieties. So there are more general algebraic varieties than algebraic varieties. Okay, so essentially there are varieties which you can think of them as being locally affine varieties. You see algebraic variety. So it means that it has a covering by affine open subsets. And then you can define regular functions. They are just those functions on Z which are regular exactly in this meaning when you restrict to this open subset. Okay, which means that they're just polynomials. So you have your variety, and these regular functions are polynomials when you restrict them to some open subset and embed this open subset in some affine space. So the point is that you can have some, and this will be important in this discussion, you can have an affine algebraic variety, but you see it as an algebraic variety, and you a priori don't see it as being defined by polynomial equations. So a typical example is take y equals c star inside C. So you take the affine line and you just forget one point. So this is not defined by polynomial equations, of course. So it doesn't look like affine, but it is an affine variety because you can look at it inside C2 as the space of as being defined by the equation xy equals 1. Okay, this is clearly isomorphic to it. Okay. And you see that in this situation, so what are the regular functions on y? So we can just take any polynomial in x and y and restrict it to y. We will get all the regular functions. If we try to do this from the first picture, this will not work because we have so if we have the coordinate z here, we can look at the function 1 over z. It's an algebraic function on y. It is not a polynomial. Okay. But of course, if you look at it as a restriction on C2, if you start from C2, you have 1 over x equals y, so which is a polynomial. Okay. So in this picture, you don't see all the regular functions as restrictions of polynomial functions on your space. Okay, so that's an important issue. Okay, and that's exactly one of the problems we will meet in a second. What do I want to say? Okay, great. So now what you can remark is that you can use this surjectivity property. Okay, if we know that on a closed subset of V, every regular function is the restriction of a polynomial. So suppose that so suppose that we have the Zaleski closure of the paired permanent contained in the Zaleski closure of the determinant of the orbit of the determinant, so inside this space Vn. So then we have surjective maps. Okay, so we can look at regular functions on these two orbits. So this will be surjective. The same for the other one, so that's always true. The surjective map. But
the closure surjective.
Thank you. And now if we have the inclusion of the map factors. Okay, if we have the inclusion, we get this extra map. Okay, because when we restrict from here to here, we can just restrict from here to here, and then to here. So that's the whole point. If you sorry?
It's subjective.
And surjective. Very important. Okay, so that's the picture. And then, so as I said before, what we really understand is not the orbit closure. We don't know what happens when we take the closure, but we still have the orbit, and when we have a function on the closure, we can restrict it to the orbit itself. And these maps, so we could hope that these maps are good approximations. What we can say a priori is that these maps are injective, because this is an open subset of the closure. So if you have a function which vanishes on an open subset, it is 0 everywhere. So we have injective maps like this. So the strategy is roughly this. If we have this inclusion, then we will have this surjective map, and we will try to get some consequences from the fact that we understand precisely these two spaces. So I will discuss these spaces in a second. Okay, so maybe I can... So maybe write it more formally. So we can suppose that. So what do we know? So G, remember, this is the linear group in S squared plus 1 variables. So it is a group whose representation theory is very well known. Representation theory. So it's part of a family of groups that behave more or less like finite groups. Okay, so more or less like. Okay, so there is a family of groups called reductive groups that include the finite ones and the general linear groups, and the representation theory is let's say easy to describe. So there are. So maybe I should. I don't know if it's clear for everybody. So, but representation. A representation of G is just a vector space W on which G acts in some way. Okay, which means that there is a morphism from G to the set of linear transformation of W. Okay, so you can realize your group by matrices acting on this space W. And one of the points is to try to understand how you can do that up to isomorphism. So there is a notion of irreducible representation. So that's essentially, so if you think in terms of matrices, it said that you cannot reduce your matrices in some way that would give a block of 0, so there is no subspace. Okay, means that there is no subspace preserved by G. So the basic representations are really those which are irreducible. And these kind of groups, finite groups or general linear group, has this very nice property that every representation is a direct sum of irreducibles. So if you want to understand representation, you have just to understand these irreducible representations. And then there is a general theory. They're encoded by some combinatorial data. Okay, so let's forget it. So for Jelen, Christian explained this in some detail. But let's forget it for a while. So what we can simply observe is that this kind of, since we have here an orbit closure, so there is this group action on the variety. So we have an induced action on the functions on this variety. And so this is a representation of the group G. So infinite dimensional, but still finitely generated. So we can decompose it into irreducible representations. So we know that there is some decomposition. So we can a priori decompose. So the space of functions on the orbit closure as a G representation. So again, we take this representation and we split it into irreducible representation. Irreducible representations are encoded by combinatorial data. And so we can just look at each irreducible representation and see how many times it appears in this representation. This will be the multiplicity. So we have a decomposition. Sum over all the irreducible representations. Of sum, so there will be V, and there is some multiplicity. Okay. A negative integer. We have this. And the same for the orbit closure of the padded permanent. A priori, we have some decomposition. Sorry?
How do you know that it's finite? In case of each representation.
I will tell you by some finite generation implies it's finite. And we can give you a bound in a second. So we have the same kind of decompositions for the padded permanent.
Maybe it's a bit dangerous to call this irreps V. There is a possible confusion with the C sub n. Just to avoid this, maybe it's better called W. Thanks.
Okay, and now we have this map, which must be surjective. And it follows from from general results on grooves. There's a Shor's lemma, for those who know, that this map will send each irreducible representation either to 0 or the same irreducible representation. Okay, so if we have a surjective map like this, it must be surjective on each of this factor. Okay, so we can have obstructions to surjectivity when the multiplicity here is bigger than the multiplicity here. If this happens, for sure the map we cannot have a surjective map like this. Okay, so obstruction to the existence of this map. Let's call it star. Can we find some irreducible representation W such that the multiplicity coming from the determinant is smaller than the multiplicity coming from the padded permanent? If we can show there exists a W again, there cannot be a surjective map like that. And so maybe a strong obstruction, suggested by Ketal. Let's be optimistic and can we find some W such that this multiplicity is 0? And the other one is positive. Which is more optimistic, but maybe so nicer in some sense because well, these multiplicities are difficult to compute, but hopefully you can find some criteria that ensure that they will vanish. So that's a strategy. Can we find some basic strategy? Can we find some representations for which this difference in the multiplicities prevent the map to be surjective, and so the orbit closure to be one of the orbit closures to be contained in the other one? Any question?
You know that multiplicities are for determinants bigger than from permanent. Does it mean that you can conclude from here that orbit closure of permanent is included in orbit closure of determinant?
No, of course not. If the multiplicity here is bigger than multiplicity here, does not mean that there is a surjective map.
Or even more, that map is surjective. there is a surjective map, but maybe it's not that.
Yeah, it may not be a ring map.
Yeah.
Or that map.
But what is really nice is that we wanted to exclude the possibility to have this permanent inside the orbit closure, and now we have something positive to do. We have to construct some representation and control their multiplicities and ensure that this property holds. So we have turned to positive problems and find abstractions. Okay, so let's try G. Okay, so we have to control these multiplicities. So, and again, what we would like to do is use the fact that we control this. It is better than we control this. So the point being that, so G that n, so I said it is an orbit. Okay, so just apply the group to a point. So there is a part of the group, there is a subgroup which does not affect the point. So there is a stabilizer. Okay, so we have a map like this, if you wish. G. So H is stabilizer. So it's okay, so it's clear what it is. It's a group of elements for which nothing happens. You don't change, and then you have that's the kernel of this morphism. So that, in fact, you can see this orbit just as a quotient of G by the subgroup H. The effect of applying G to that n is simply to kill this stabilizer subgroup. So suppose that H equal 1. So if we look at the, we just have the orbit will be isomorphic to just the group G, and then we know that what this is. Because as I told you, these groups, this kind of group behave very much like finite groups, and we've seen yesterday that for finite groups there is this well-known decomposition of the regular representation as a product of matrix algebras, and this is also what happens in this case. So this is the well-known result due to Peter Weil, that this is the direct sum over the irreducible representations of the endomorphisms of W. Okay, so now we have infinitely many matrix algebras, but still the result is true in general. Okay, which I will write as a sum of W tensor W dual tensor W. Okay, and so notice you have a direct tensor product of representations of G. So G appears twice because there is here an action of G cross G. Okay, when you have a function, f a function on G, you can modify it in two different ways by applying the group, either on the left or on the right. Okay, you can apply G prime f, get a function which on x would be f of G minus 1 x. Oh, sorry, it's on this side. Gx G prime minus 1. Okay. So the group can act either on the left or on the right when it's not commutative. So you have an action of G cross G, and one of the G acts on the first factor, and the other G acts on the other one. Now when you go to the G mod H, what does happen? Okay, so of course when you have a map function on G mod H, you can pull back to G to get function on G. So we have something inside this direct sum. And the fact that you bound it out by H just means that it must be invariant by the left action of H. Okay, so this you just look at the functions which are invariant by the right action of H. The right action is here. So you get exactly the sum over the irreducible representations of W star times, it is denoted like that, the H invariance in W. Okay, so what you should think of. So now there is no action on G anymore here on the right. So it's just means that the irreducible representation W star appears with multiplicity equal to the dimension of this WH. So we have some control on this. So then the question is, how do we pass to the orbit, to the closure? Okay, because you have, so again, we have these two embeddings, which can be for the orbit of the determinant or the padded permanent. Goes as well. And so how can we compare the regular functions on these two varieties? So there's this issue that I mentioned some time ago, that this is a closed algebraic subset of the space denoted by Vm. So I have a surjective map. I can represent any regular function here by some polynomial. But this is not true anymore for the orbit. Okay, this is not Zariski closed. This is never Zariski closed because you have, in particular, in G, recall G is the general linear group, so you have the homothesis. You can just apply homothesis to get any point to 0. 0 is not in this space. Okay, so we don't know, and it will not be true in general, that regular functions here can be represented by polynomials. So we can try to, we have this problem coming essentially from the homothesis, and so we can try to get rid of them by looking not at the GL, but SL. If we stick to SL, we will kill essentially all the homotheses. So let's call G prime the group SL n squared plus 1. And inside this, we have the which will be the G prime orbit of the determinant or the padded permanent, yes?
Sorry, what is this word homothesis?
Sorry? Scaling. So we still have some way to scale, but only finitely any possibilities. So at least we no longer have this problem that 0 will be a priori in the closure. Or we could be, but we have no hope. Okay, so H prime is the intersection of H with G prime. Okay, so the question is this one Zariski closed? Okay, because if it is Zariski closed, then we can we have some control on this, and this and this are more or less the same up to scalars. We can compare them. So the good news are that so the G prime orbits of either the determinant or the permanent are closed. So we're in good shape. The bad news is that the G prime orbit, if we take the padded permanent, is not closed. So we'll have to work harder in this case. But still, so let's consider the determinant and see what we can deduce from the fact that it's closed.
Sorry, in the first statement, do you mean perm n or perm n?
N. So if you don't pad, if you don't multiply by linear form, the orbit is closed.
Easy to see what it's closed? Is it easy to see what there is like some reason why it's closed?
There is a classical theorem by Kempf that when the orbit is not closed, this is because it must be because there is some preferred space. In general, when you take a point in a space and the group acting, if the orbit is not closed, there must be some special subspace, okay, which is privileged by your point. Yes.
I have another question. So, perm and the padded permanent might be in the closure of the G orbit of that, but not in the closure of the G prime orbit. Because it's something smaller, or why would this be okay to study?
Not in the G prime.
Because it's a smaller set.
Yes, but you're dispadding, so you can just multiply by anything.
Oh, I see. You're claiming you could just scale it.
Yes, you
Put it
can.
there.
Okay.
So the representation there
does
would
not
be
make
different.
it.
Okay.
Okay, so for the determinant, and so the orbit is closed, so G prime or H prime is closed. And so we have, so again we have this map, which will be surjective, and the other one, the orbit closure G, which will also be surjective. So we are pretty much in the situation of the hyperbola. I mentioned at the beginning. Hyperbola like this would be G prime over H prime, which is closed. But when you take the cone over the hyperbola, which is G over H, then it's no longer closed. You have the whole plane minus the two axes. So that's the typical phenomenon that we have to understand. So an important thing to mention is that, so here, this is the space of polynomials, so it's graded by the degree. And since here we have a cone, this is also graded by the degree. And this map is graded. But this one is not a cone anymore, so there is no grading here. But still what we can do is, we have also a restriction map here. Since this is obviously a subset over here, which is surjective. Okay, so remember that this we understand very well. This is what we try to understand. So we have the surjectivity. Let's call this phi for surjective. And now we can restrict to each degree. Restrict to degree d polynomials. Okay, so what does that mean? We have a polynomial of degree d. Suppose we have something which polynomial of degree d that vanishes here. So we have a polynomial in the cone over this variety. It vanishes on it. Since it's homogeneous, it will vanish everywhere. So this map is in fact injective. That's why we have a good control of this. We have the surjectivity and the injectivity in each degree. And the consequence is that if you plug in the formula given by the Peter-Weyl decomposition applied to G prime, is that a G prime module, an irreducible G prime module, G prime liberal representation W appears in what we want to understand if and only if the space of invariance is non-zero.
Does it close about multiplicities also?
Sorry?
Does it close about multiplicities also? Like it's
No, we don't have a good control of the multiplicity because we have a. So this map is subjective, but you could lift an irreducible G prime module in 2 different degrees. So this could modify the multiplicities in some way that we don't understand. But at least we have a criterion to decide whether the multiplicity is 0 or not. Okay? And this is and you want to understand abstraction, this is an important issue. So now that's essentially the program. Fine. So again, on abstractions. So still we have this issue that I'm forgetting that the orbit of the Pellet determinant is not closed, but it's not too far from being closed, or at least we understand why it is not closed, so we can get some information from this. That's more technical, I don't want to talk about that. So we have to understand now the invariance, to understand the H prime invariance for the determinant of the permanent. And the nice fact is that this, so we understand this group pretty well, it's in the homework, if you manage to. So the exercises, so the stabilizer of the determinant.
I can understand well.
Okay, so is so there are 2 ways to transform a matrix in a way that preserves the determinant. So multiply by 2 matrices on the right or the left. Product of the determinant being 1. It's the same with and transpose X. So you see that the stabilizer, in this case, H is GLN cross GLN, product by Z2. So nice group, and for the permanent, okay, so the permanent, the stabilizer is it's a bit more complicated.
Don't you need to scale to make sure you get determinant for that as well?
Sorry?
It's better to write SL cross SL.
But it's somewhere in between the two.
Yeah.
Yeah, well, if you look at the image, it's really smaller than even SL cross SL, but it's safer to write
I
SL.
prefer to write it like that. So it's not. You can make some adjustment. Ah, yes, right. I mean, there's some question. So for the permanent, you get some product of two groups which are generated by permutations and diagonal matrices. So matrix permutation matrices with some coefficients. So when you try to, what is really striking is that when you try to understand multiplicities, so at least when you find abstractions, we need to decide whether we have this kind of invariance. And for determinants, so the existence of abstractions is related to very old mathematics.
Laurent, I think you forgot something important. With the stabilizer of the permanent, you have the symmetric group between, right?
Permutations and diagonal matrices.
Permutations and
this is
diagonal
your
But you also
it's
have-
not torus, but
Yeah.
it's in the
And you also have the Z2 there,
It's
but
not
that was
torus.
not so
Sorry, I
important.
was confused by thinking Tn is torus.
No, it's the monomial matrices.
Monomial matrix, there.
No, but there is a Z2.
Okay.
permutation matrices with coefficients.
I agree. Problem, what's the problem? Okay.
The existence of Ruplicht is related to representation of symmetric groups. Okay, something really fascinating. And in the end, at some point, you need to understand representations of the most basic group, symmetric groups, in particular Kronecker coefficients. You have to decide. Whether Kronecker coefficients can be zero. So then special Kronecker coefficients. Kronecker coefficients mean being the multiplicities you get then when you take two representations of the symmetric groups, and take pi and sigma, reducible representations of Sn. So we take a tensor product. This will split again as a sum of representations of the symmetric group again with some multiplicities, which are the Kronecker coefficients. And then we need to decide whether certain of these Kronecker coefficients are zero, and for what reason they must be zero. Okay, so again, that's very nice. That's great because these Kronecker coefficients have been studied for years. Huge amounts of results on them. The bad news is that what we would need to understand seems to be still very much out of reach. It's completely beyond what is known today about these coefficients. But still, this motivates some very interesting works of work.
mean, are there simple examples where you can show obstructions in any sense? Like, I mean, I have no idea how you prove such an obstruction exists. Like, I guess I have in mind in the sense of, you know, we do have some examples, maybe not for determinant, but other polynomials where you can show that the one closure is separated, which have natural, like, algebraic circuit motivation. And we have the lower bounds, like, can you upgrade them to obstruction?
Yeah, so what is really interesting is that you can use this approach in some different problems. And there has been some cases, not yet for this problem, but for other problems, typically for matrix multiplications. There's been some work on device on obstruction in this very sense, which allows to bound the lower bound for the rank of matrix multiplications.
I guess to me, even that is a very, like, that's also sort of a hard problem, like matrix multiplication. I mean, it seems like there should be easier things.
Yeah, so the bounds are far from being optimal, and they're not best. Still hope to improve them, and this gives hope for this problem.
Do you have an explicit, easier problem in mind?
Like, just take like x1 to the d plus dot dot dot, you know, xm to the d.
Yes.
Or d, I guess, equal to n. So you consider, you know, the affine changes of projections of that polynomial. And you can show that, like, that cannot compute the determinant. You need many, many, many things. And, like, that's a very easy thing to show if you know the relevant literature. And so it's sort of like, you can imagine, you know, promoting that lower bound, because there's a sort of idea like the rank argument, say the dimension of some, you know, partial derivative space is large for the determinant or permanent, but it's small for these sorts of things. So that gives you an explicit, you know, separation of the polynomial. You could hope to show, well, can we use representation theory to say, let's promote that to an abstraction lower bound.
The problem is the group for that is so small that it's going to be hard to do. I mean, the one thing that sort of makes this more tractable, especially for the determinant, is the group is very, very large. So it's harder to have invariance.
Sorry, so which group, the symmetries of the determinant?
Yes.
Okay.
So it makes it easier to have invariance because the group is large, whereas the smaller group, sorry, I said it the other way around. You have too many invariants if your group is really small.
Yeah, at some point we want some multiplicities to be zero, so you have to show that you don't have invariance under your group, so it's better if your group is large.
So you mean the power sum, x1 to the d plus xn to the d.
Right.
Yeah, I think that's a very good test case. But even
even
for that, really it's not easy to understand all these multiplicities.
It could be interesting. There are symmetric groups.
Yeah, it's not easy to analyze that.
Last time we have shown that permanent cannot be computed by determinant of size and square over 2.
Yes.
Can it be shown in the sense of abstraction, or can you show that it's not? It cannot be shown in like this approach.
Yeah, no, it's
that module is not abstraction.
Ah.
Yeah, but still we could hope to recover some results using abstraction. We have very few results about these Kronecker coefficients. So we need to control special types of Kronecker coefficients, and the intuition was that it was very hard to expect any Kronecker coefficients to be zero. It seems to be very uncommon. And so we have new hopes thanks to Ketan to prove that must exist many Kronecker coefficients equal to zero. Still, we have very few control on what these Kronecker coefficients are, and especially those that are especially relevant in this case. There is no concrete result yet in this situation coming from this approach.
Can you briefly say in which places these reductions you do are not tight?
Or not?
So you do a series of reductions. You make the problem, right? You have the initial problem, like asking whether the permanent is in the order of the determinant. Then you do a series of reductions, and you end up with this problem. Could you briefly say where there's maybe large gaps? And, you know, it's
well, essentially,
we can solve the original problem with this approach. This question is more difficult than the original question. It's a stronger conjecture.
Yes, it's a strong conjecture, but how much stronger is it?
and really, what would really say that the permanent is in the closure of the determinant is the fact that we have this surjective map. So there are two reductions used. As for abstractions, they are just numerical abstractions coming from multiplicities. So the first reduction, which is that you cannot have this surjective map when the multiplicities do not fit, one is bigger than it could be. And then second reduction would be that you ask the multiplicity to be 0, which is easy way to test. So these are the main two reductions. But really the fact that the permanent is in the orbit closure is really equivalent to the existence of this surjective. So then there is another point, which is that the closure is not exactly what we want. But it's,
Okay, if there are no further questions, then I suggest that we think Laurent again. And we will reconvene at 10:45. Okay, so the closeness of these orbits is a simple Hilbert map for it.
yes, this Kemp's criterion has consequences.
Oh, you need second or just Hilbert map? You just need to show that. That's enough.
Because
so you don't
I was
need
able to
this
prove it
best
before I
thing
knew
that-
about Kemp.
I see.
Yeah, okay, so did you finish the
Yeah, yeah.
I'm sorry?